My name is Minakshi from BSc Chemistry Honors third year. Today, my topic for visually impaired students video is synthetic polymers of organic chemistry. Introduction. Polymers form the backbone of modern civilization and are the chief products of modern chemical industries in almost all walks of life, starting from household utensils, clothes, furniture, etc., to automobiles to space aircrafts and biochemical and surgical operations. Polymers are extensively used. Polymers, Greek poly means many and mers mean part, are very high molecular masses substance, each molecule of which consists of a very large number of simple structural units joined together through a covalent bonds in regular fashion. The simple molecules from which the repeating units are derived are called monomers, and the process by which these simple monomers are converted into polymers is called polymerization. For example, polythene is a widely used polymer which is obtained by the polymerization of a monomer ethylene or ethene CH2 double bond CH2. Besides the repeating structural units, a polymer generally contains two types of end groups. For example, in case of polythene, these end groups are CH3CH2 ethyl and ethanyl CH2 double bond CH groups. Thus, the polythene may be completely represented as CH3CH2 having a repeating unit in mid, CH2 single bond CH2 N, and on the right side CH2 double bond CH double bond CH2. The nature of the end groups, however, depend upon the method of preparation of polymers, and in many cases, the structure of end groups are not known with certainty. Therefore, polymers are generally written in terms of recurring units only. Polymers and macromolecules. The term polymers and macromolecules are often used without any distinction, but strictly speaking, all polymers always consist of 100 to 1000 of repeating structural units, but macromolecules may or may not contain repeating unit. For example, chlorophyll is a macromolecule but not a polymer because it does not contain any repeating structural units. Similarly, protein and nucleic acid should be regarded as macromolecules but not polymers since their molecules do not contain repeating structural units. In contrast, polythene may be regarded both as a macromolecule as well as a polymer since it contains a large number of repeating structural units. Thus, all polymers are macromolecules but all macromolecules are not polymers. Although protein and nucleic acids are macromolecules, they are usually called polymers. This is due to the reason that proteins are made up of large number of alpha amino acids, which if not structurally are chemically similar. Similarly, nucleic acids are made up of large number of nucleotides which are also chemically similar. Homopolymers and copolymers. Depending upon the nature of repeating structural units, polymers are divided into two categories, homopolymers and copolymers. Homopolymers, polymers whose repeating structural units are derived from only one type of monomer units are called homopolymers. For example, in case of polythene polymer, which is obtained by the polymerization of ethylene molecules, the repeating structural units CH2 single bond CH2 is derived from one type of monomer, that is ethylene, shown by the reaction N CH2 double bond CH2 ethylene, and that is a monomer. On polymerization gives polythene a polymer. Other example of homopolymers are polypropylene, polyvinyl chloride, polyisobutyrene, neoprene, PAN, polyacrylonitrile, nylon 6, polybutadiene, Teflon, cellulose, starch, etc. Copolymers. Polymers whose repeating structural units are derived from two or more type of monomer units are called copolymers. For example, in case of nylon 66, the repeating structural units NHCH26 NHCO CH24CO is derived from two monomer units, that is hexamethylene diamine and adipic acid. Hexamethylene diamine, a monomer, plus adipic acid, a monomer, on polymerization give nylon 6,6 polymer. Other example of copolymers are buna-S, polyester, alkylide resins, bakelite, melamine, formaldehyde polymer. Classification of polymers. Depending upon the source from which they are obtained, polymers are broadly divided into three classes: natural polymers, semi-synthetic polymer, and synthetic polymers. Natural polymers, the polymers which are found in nature in animals, plants, are called natural polymers. Protein which make much of our body, nucleic acid which control heredity at molecular level, cellulose which provides food, clothing, shelter, and rubber which is used for making various articles of daily use are all natural polymers. Semi-synthetic polymers are mostly derived from naturally occurring polymers by chemical modifications. For example, cellulose on acetylation with acetic anhydride in presence of concentrated H2SO4 gives cellulose diacetate, which is used for making threads of acetate rayon and other materials like film glasses, etc. Vulcanized rubber, which is superior to natural rubber, is extensively used for making tires. Gums, cotton, gun cotton, which is cellulose trinitrate, is used for making explosives and smokelace powder. Synthetic polymers. A large number of man-made polymers are now available. These include fibers, nylon, polyester, plastic, polythene, polypropylene, rubbers, neoprene, polystyrene, which are widely used for clothing, electric fittings, eye lenses, and substitute for wood and metals. In this unit, we shall discuss only synthetic polymers. Preparation of synthetic polymer. The properties of synthetic polymer depend largely on the extent of polymerization. Therefore, to prepare polymers of desired properties, it is essential that the monomer used in polymerization must be of highest purity. The condition of the reaction must be carefully controlled. This is because the reaction involved in the process of polymerization must proceed in almost quantitative yield. Any impurity, if present, may initiate an undesirable side reaction which may stop the polymer chains from growing further and thus prevent the formation of high molecular mass polymers. The process involved in the synthesis of polymer can be broadly divided into two categories: addition or chain growth polymers, condensation or step growth polymerization. Addition or chain growth polymerization. In this type of polymerization, the molecules of same or different monomers simply add on one another, leading to the formation of a macromolecule in which the molecular formula of repeating structural unit is same as the starting monomer. The polymers thus formed are called addition polymers, and these are also called chain growth polymers. Addition or chain growth polymerization generally occurs among molecules containing carbon-carbon double bonds. The reaction is started by suitable initiator which adds the carbon-carbon double bond to form a reactive intermediate. This reactive intermediate then adds to a second molecule of the monomer to form a new bigger intermediate, which in turn add to third monomer molecule, and so on. In this way, the polymer chain keeps on growing by successive addition of monomer molecules one at a time to the reactive end of the chain. This is why process is called chain growth polymerization. Since most of the monomers used in addition or chain growth polymerization are monosubstituted alkenes or vinyl derivatives, Therefore, the addition or chain growth polymerization is also called vinyl polymerization. Some of the most important polymers formed by vinyl polymerization are polythene, polypropylene, polyvinyl chloride, polyacrylonitrile, polystyrene, polymethyl methyl acrylate. Depending upon the nature of monomer taken and initiator used in the above polymerization, the reactive intermediate may be a free radical carbocation carbanion. Therefore, vinyl polymerization occurs by three different mechanisms. Let us now discuss in detail the mechanism of addition or chain growth polymerization by starting with free radical and vinyl polymerization. Free radical vinyl polymerization. Most of the commercial addition polymers are vinyl polymers which are obtained by polymerization of alkene derivative. This type of polymerization is carried out by heating the monomer with a small amount of radical initiator or by subjecting the monomer to ultraviolet light. These initiators are molecules which decompose to form radicals easily. Tert butyl peroxide, benzoyl peroxide, hexadiosub diisobutyronitride are commonly used initiator because they decompose under mild condition to form radicals. Tert butyl peroxide reacts at 373 to 423 Kelvin gives tert butoxide radical, which benzoyl peroxide on heating gives two benzoyl oxy radicals. Azide isobutynitrile on heating gives isopropyl nitrile radical. Like all other free radical reactions, free radical polymerization also occurs through the following step: initiation, propagation, and termination. Chain initiation step: the initiator on heating decompose to form initiator free radical. The process of polymerization starts with the addition of this initiator free radical to double bond of alkene monomer to form a new radical of larger size. These are called chain initiation steps. Initiator on heating gives two radicals, free radicals. Chain propagation steps. The addition of radical 1 to another molecule of alkene generates yet another big sized radical. The repetition of these sequence with a new and bigger sized radicals propagates the reaction, and these steps are called chain propagation steps. Chain termination step. Eventually the polymer chain is terminated by the reaction that consumes these radicals either by combination step 1, or disproportionation, step 2. Many other simple and substituted alkenes such as polypropylene, vinyl chloride, styrene, tetrafluoroethylene, acrylonitrile, methyl acrylate, with vinyl acetate undergo radical polymerization. Chain transfer agents. Competing reaction in vinyl polymerization. We have discussed above that during vinyl polymerization, the termination step involves either combination or disproportionation of growth radical chains. However, the growth of original polymer chain may also get terminated or interrupted in presence of certain compounds such as CCl4, which compete with the monomer for growing polymer chain. At the same time, such a compound produces a new free radical which may initiate its own new polymerization chain. The overall effect of such compounds on the process of polymerization is that the polymer formed has a lower average molecular mass. Such compounds which brings about termination of the original polymer chain with the simultaneous initiation of another polymer chain are called chain transfer agents. For example, in presence of CCl4, styrene undergo polymerization at the same rate in its absence, but polystyrene formed has a lower average molecular mass. Furthermore, it also contains small amount of fluorine. This may be explained as follows: the growing polystyrene radical, which would normally react with another monomer molecule, instead reacts with chain transfer agents To terminate the original chain, a new free radical produced initiates a new polymerization chain I incorporation chlorine atom. Thus, since one reaction chain is replaced by another, the rate of polymerization is unaffected. Further, since average number of chain propagation steps in each reaction chain is reduced, the average molecular mass of the polymer decreases. Chain inhibitors. If chain transfer agent forms a radical which are highly unreactive, the original chain reaction get terminated without a new being initiated. As a result, the process of polymerization is inhibited, and such a chain transfer agent which inhibited the process of polymerization are called inhibitors. Many amines, phenols, and quinones act as inhibitor. Since even traces of impurities of chain transfer agent or inhibitors can interfere with the polymerization process, therefore monomer used should be highly pure organic compounds. In extreme case, if the monomer is of low reactivity and chain transfer agent is of high reactivity, then no polymerization occurs. Instead, addition of chain transfer agent occur across the double bond of the monomer. Ionic vinyl polymerization. This type of vinyl polymerization proceeds through the ionic intermediates instead of free radicals is further classified as cationic vinyl polymerization and anionic vinyl polymerization according as carbocation and carbanion respectively are the intermediates as described below. Cationic polymerization. Certain alkene monomers can be polymerized by cationic mechanism as well as by free radical mechanism. Cationic polymerization, like free radical polymerization, occurs by a chain reaction pathway in the presence of strong protonic acids such as H2SO4 or Lewis acids such as AlCl3 and BF3 in presence of trace of water as inhibitor. In chain initiation step, the proton add to double bond of the monomer to form carbocation. Propagation step, the electrophile addition of this carbocation intermediate occurs at to the double bond of another monomer molecule to form a bigger carbocation. This sequence of steps is repeated over again to form polymeric carbocation. In the chain termination step, the loss of protons from the polymeric carbocation occurs to complete the polymerization. Evidently, greater the stability of carbocation intermediate, more facile is the cationic polymerization. Thus, alkene containing electron donating groups are preferably polymerized under cationic conditions, though free radical polymerization can also occur. In contrast, monomers such as vinyl chloride, acrylonitrile, which contain electron withdrawing group, do not polymerize well in these conditions. This is because the presence of electron withdrawing substituent destabilizes the carbocation intermediate. Here, the electron donating methyl group stabilize the carbocation intermediate one. Polyisobutylene is a tacky material and is used for making adhesives. Anionic polymerization, alkene monomers with electron withdrawing substituent like C6H5CnCOR can be polymerized by anionic mechanism as well as by the free radical mechanism. Anionic polymerization, like free radical polymerization, occurs by chain reaction pathway in the presence of strong bases such as NaK positive and H2 negative, lithium positive and H2 negative organometallic compounds such as N-butyl lithium as initiators. In the initiation step, the bases add to the double bond of monomer to form a carbanion. In the propagation step, these carbanions add to another monomer molecule to form a bigger carbanion, and the process gets repeated over again and again to form a polymeric carbanion. This chain reaction is finally terminated by addition of a proton. Some alkenes are also easily polymerized even by weak bases. For example, methyl alpha cyanoacrylate, because of presence of two powerful electron withdrawing groups CN and CO2, CH3 quickly undergoes polymerization even in presence of basic impurities such as metal oxide present on the surface of ordinary glass to give a super glue or crazy glue. It has high tensile strength. One drop of it is claimed to support weights of 2000 IBS. Evidently, greater the stability of carbonyl intermediate, more facile is the anionic polymerization. The alkenes containing electron withdrawing groups such as acrylonitrile, methyl acetates, acrylates, styrene, etc., can be polymerized under anionic conditions, although free radical polymerization is commercially preferred. Limitations of vinyl polymerization. Although vinyl polymerization can take place by free radical or ionic mechanism, it is usually carried out by using free radical initiator. This kind of polymerization suffers from the following two drawbacks. Branch structure of polymer. Free radical polymerization does not give the linear polymers but instead gives branch chain polymers. The presence of these branches influence the properties of polymers. In general, the branch chain polymers do not fit closely and hence have lower melting points, low degree of crystallinity, and have weak mechanical properties. Stereochemistry of polymers. A free radical vinyl polymerization involves head-to-tail union of monomer units. As a result, the substituent groups G appears on the alternate carbon atom of the polymer chains. Depending upon the relative position of group G on the polymer chain, the three stereochemical arrangements are possible are given below. Isotactic. Iso means same, tactic means order. In this arrangement, all the substituent groups lie in the same side of zigzag chain. Syndi Syntactic means alternating order. In this arrangement, the substituent groups regularly alternate on opposite sides. Atactic means no order. In this arrangement, substituent groups are randomly oriented. For any particular polymer, these three stereoisomeric forms have somewhat different properties. In general, the isotactic and syndioctactic polymers fit together well and have high degree of crystallinity. They have high melting point, have stronger mechanical properties, and form a strong fiber. In contrast, atactic polymers are soft, elastic, rubbery materials. By proper choice of experimental conditions such as catalyst, temperature, solvent, etc., of these stereoisomeric polymers can be prepared. Free radical vinyl polymerization generally gives branched atactic polymers. However, isotactic and syndiotactic polymers can be made by use of a special Ziegler-Natta catalyst. Ziegler-Natta polymerization. Until 1953, almost all vinyl polymerization were carried out by free radical initiators. Since then, a new kind of polymerization called coordination polymerization was introduced by Carl Ziegler and Giulianatta, who jointly received the Nobel Prize in 1963 for this work. Coordination polymerization is carried out in the presence of Ziegler-Natta catalyst, which consists of a titanium trichloride or tetrachloride and an alkyl aluminum compound. The most commonly used catalyst of this type is mixture of triethyl aluminum and titanium tetrachloride in an inert solvent such as heptane. The solution is then heated for an hour. There are three main advantages of using Ziegler-Natta catalyst. Polymerization takes place under a relatively milder condition. The polymers obtained are linear with almost no branching. The polymerization occurs in a stereospecific manner. It is possible to prepare either the isotactic or syntactic polymers by proper choice of Grignard catalyst. Mechanism: when triethyl aluminum and titanium dichloride are mixed, they form a titanium complex holding an ethyl group. When an alkene, say ethylene, is added to this mixture, it forms a coordination complex with a transition metal titanium by donating its pi electrons. The pi cloud of these alkene overlap with the empty orbitals of titanium. Now both ethyl and ethylene molecule are held by the metal. An insertion reaction occurs in which the ethylene molecule is inserted between the metal and the ethyl group. In other words, instead of ethyl, there are now n butyl group attached to titanium. The binding site where the ethylene was held earlier is now vacant. Another ethylene molecule gets pi bonded to the metal and then insert itself between the metal and the n-butyl group to form its this time an hexyl group. So the process continues over and over again with the alkyl group growing two carbon atoms at a time. Ultimately, the insertion of hydrogen occur either by hydrogenation or by beta elimination, and the molecule polyethylene get separated from the metal. By proper choice of experimental condition, the propylene can be polymerized to give any of the three stereoisomer: isotactic, syndiactic, and atactic. Some of important vinyl polymers: polyethylene or polythene. It is widely used addition polymer and was first prepared by free radical or high temperature polymerization of ethylene. However, these days two types of polythenes are produced which have widely different properties: low density polythene and high density. Low density polythene, it is manufactured by heating ethylene to 350 to 5570 Kelvin under a pressure of 1000 to 2000 atmosphere in the presence of trace of oxygen or peroxide. This polymerization occurs by the free radical mechanism and mechanism which is initiated by the oxygen or peroxide. The polythene thus produced has a molecular mass of about 20,000 and has highly branched structure. This branching occurs due to chain transfer of special kind in which the chain transfer agent is a polymer molecule at a high temperature at which the polymerization occurs. The growing free radicals not only add to the double bond of monomer but also abstract hydrogen from the chain already formed. The abstraction generates a new free radical center from which a chain can now grow as shown below. These branched polymer molecules do not pack well and hence this type of polythene has a low density and low melting point. This is why polythene prepared by free radical polymerization is called low density polythene. Property and uses: low density polythene is a transparent polymer of moderate tensile strength and high toughness. It is chemically inert, slightly flexible, and of poor electric conductivity. It is widely used as a packing material, as insulation for the electrical wire cables in the manufacture of squeeze bottle toys, flexible pipes. High density polythene. It is prepared by the coordination polymerization of ethylene. In this process, the ethylene is heated to 330 to 350 Kelvin under a pressure of 1 atmosphere in presence of a catalyst containing triethyl aluminum and titanium trichloride or tetrachloride, Ziegler-Natta catalyst. The polythene thus produced practically consists of a linear chain of polymer molecules. These polymers molecule pack well and hence this type of polythene has a high density and higher melting point than the polymer produced by the free radical polymerization. This is why polythene prepared by the coordination polymer is called high density polymers. Property and uses: high density polythene is a translucent polymer. It is also chemically inert but the great toughness, hardness, and tensile strength has low density polymers. It is used in the manufacture of containers like bucket, tubs, housewares, pipe, bottle, and toys. Polypropylene or polypropene. Polypropylene is prepared by heating propylene in the presence of trace of benzyl peroxide and radical initiator by Ziegler-Natta catalyst. It exists in three isomeric forms: stereoisomeric forms, isotactic and diatactic and atactic. Free radical polymerization usually gives branch chain and atactic polymer. However, the linear polymer polypropylenes can be prepared by using Ziegler-Natta catalyst. Uses: it is harder and stronger polymer than the polythene and is used for packing the textile and food, for making liners for bags, heat shrinkable wraps for records and other articles, for making automotive molding, seat covers, carpet fibers, ropes, etc. in the manufacture of stronger pipes and bottles. Polystyrene or styrene. Polystyrene can be prepared either by free radical polymerization or by using Ziegler-Natta catalyst. Free radical polymerization gives atactic polymers softening at 358 Kelvin, while Ziegler-Natta polymerization gives isotactic polymer which melts at 523 Kelvin. Both have heated to tail structure. Both have head to tail structure. Uses: polystyrene is a good lightweight material and is used for making plastic toys and household wear, telephone, radio, television bodies, refrigerator lining. Polyvinyl chloride. It is prepared by the free radical polymerization of vinyl chloride. Polymerization is carried out in water suspension which contains soap as an emulsifier or persulfate as an initiator. The monomer vinyl chloride is itself manufactured either by addition of HCl to acetylene in the presence of mercury salt as catalyst or by dehydrochlorination of ethylene. The monomer vinyl chloride is itself manufactured either by addition of HCl to acetylene in presence of mercury salt as a catalyst or by dehydrochlorination of ethylene dichloride. Uses: it is a pliable polymer and thus has very wide range of application. For example, when plasticized with high bolting esters such as di and butyl phthalate, it is used for making raincoats, handbags, plastic dolls, shower curtains, upholstery fabric, shoe soles, and vinyl flooring. Since dibutyl phthalate is slightly volatile, it evaporates slowly. As a result, soft plasticized vinyl polymer eventually loses its plasticizer and become hard and brittle. It is good electrical insulator and hence is used for coating wire, cable and other electrical goods. It is also used for making gramophone records and hose pipes. Polytetrafluoroethylene or Teflon. Preparation: it is an addition polymer, homopolymer, and is obtained by heating tetrafluoroethylene under pressure in the presence of ammonium peroxosulfate as a radical initiator. Uses: Teflon is a flexible and inert to solvents to boil acids such as even aquaresia and is stable up to 598 Kelvin. Because of its great chemical inertness and high thermal stability, Teflon is used for making non-stick utensils. For this purpose, a thin layer of Teflon is coated on the inner side of the vessel. It is also used for making gaskets, pump packings, valve seals, non-lubricating bearings, filtered clothes, etc. Polyvinyl chloride, polyvinyl acetate. Preparation: it is a chain growth homopolymer and is prepared by free radical polymerization of vinyl acetate in presence of benzoyl peroxide as a radical initiator. Vinyl acetate need for purpose is itself prepared by passing a mixture of ethylene, acetic acid vapors and oxygen over a heated catalyst consisting of PdCl2 and CuCl2. Uses: it is a soft rubber like polymer and used in making plastic emulsion paints, adhesive in making paper grease proof. Polymethyl methacrylate PMME. Preparation: it is a chain growth homopolymer of the monomer methyl acrylate. The monomer is itself obtained by treating acetone cyanohydrine, which brings about simultaneous dehydration, hydrolysis, and esterification. This upon polymerization in presence of radical initiator give polymethyl methane acrylate. Properties. It is a hard and transparent polymer. The most important property of polymethyl methacrylate is its clearness and excellent light transmission, even better than the of glass. Uses. It can take a beautiful color and tints and hence is widely used in the manufacture of lenses, light covers, light shades, signboards, transparent domes and skylights, aircraft windows, protective coating, dentures and plastic jewelry. Polyethyl acrylate. It is prepared by free radical polymerization of ethyl acrylate. Properties and uses. Polyethyl acrylate is a tough and somewhat rubber-like product. Is mainly used in the manufacture of blanket, carpet, and variety of clothes. Polyacrylonitrile pen. Polymerization of acrylonitrile in presence of peroxide as F or FeSO4 and H2O2 catalyst gives polyacrylonitrile. The monomer acrylonitrile is itself manufactured either by addition of HCN to acetylene in presence of CuCl and HCl as a catalyst or by passing a mixture of propylene, ammonia and air over a catalyst consisting of a mixture of oxides of molybdenum, cobalt, aluminum at 723 Kelvin. Uses. Polyacrylonitrile is a hard, horny and high melting material. Polyacrylonitrile forms water resistant and quick drying fibers. The fibers can be worn and knitted and can also be blended with wool. It is used in the manufacture of Oralone and acrylane fibers, which are used in making suits, sweaters, bathing suits, carpets, and blankets. Condensation or step growth polymerization. In this type of polymerization, a large number of monomer molecules combine together, usually with the loss of simple molecules like water, alcohol, ammonia, carbon dioxide, hydrogen chloride, etc., to form a macromolecule in which the molecular formula of repeating structural units is generally not the same as that of monomers. The polymer thus formed are called condensation polymers. Condensation polymerization generally occur between the monomer containing bifunctional and polyfunctional compounds. For example, the polymer nylon 66 is obtained by the condensation of two monomers, hexamethylene diamine and adipic acid, each containing two functional groups with loss of water molecules. Actually, the condensation polymerization occurs through a series of independent reactions. Each such reaction involves the condensation between the two difunctional monomer molecule and the loss of simple molecule like water, ammonia, ROH, and Cl to form dimer, which is also a bifunctional compound. This dimer may react with another molecule of one of the monomer, and the resulting product may react with another molecule of the second monomer to form a tetramer. Thus, the product at each step are again these difunctional compounds, so that the sequence of condensation reaction goes on in the polymer chain keeps on growing step by step. Alternatively, the dimers may combine to form tetramers, which in turn may combine to form octamers, etc. These molecules of moderate size then combine together to form the polymer. Since in this process the polymer is formed in the stepwise manner, it is called step growth polymer, or the process is called step growth polymerization. It may be pointed out that in contrast to chain growth polymer, the formation of step growth polymer does not occur through chain reaction involving free radical, carbon ion and carbon cations, etc. reactive chemical species. Some important condensation polymer, their preparation and uses are discussed below. Polyester. Polymers which have ester linkage are called polyester and prepared by the condensation polymerization of diacid with diols. Polyethylene terephthalate phthalate, PET, Dacron or Milo. Preparation. It is prepared by the condensation polymerization of ethylene glycol and terphthalic acid. By elimination of water, the reaction is carried out at about 420 to 460 Kelvin in the presence of catalyst containing a mixture of zinc acetate and antimony trioxide. In practice, a better product is obtained by using trans-esterification process. The dimethyl ester of terphthalic acid is heated to about 475 Kelvin. With ethylene glycol, methanol is evolved as a gas driving the reaction to completion. The molten product thus obtained is spun to Dacron or cast into a film called mylar. Uses. The mylar film is extremely flexible, tear resistant and resistant to UV degradation, therefore it is used in making magnetic recording tapes. Fiber of styrene is highly crease resistant, durable and has low moisture content. It is not damaged by pests like moth, mildew, and therefore used in manufacture of wash and wear fabric, tire cords, seat belts, seals. Also blended with cotton and wool to increase their resistance to wear and tear. Polyethylene phthalate preparation. Glyptol is a general name for all polymer obtained by the condensation of dibasic acid and their anhydrides with polyhydric alcohol such as ethylene glycol, glycerol, etc. The simplest glyptol polyethylene phthalate is formed by the condensation. Glyptol is a general name for all the polymer obtained by the condensation of dibasic acid or their anhydrides with polyhydric alcohol such as ethylene glycol, glycerol, etc. The simplest glyptol polyethylene phthalate is formed by the condensation of ethylene glycol and phthalic acid. Polyethylene phthalate is a thermoplastic. It is dissolved in suitable solvent and the solution on evaporation leaves a tough but not flexible film. Is therefore used in the manufacture of paints and liquors. Polyamides. Polyamides, polymer which have amide linkage are called polyamides. These are prepared by the condensation polymerization of dibasic acid with diamines and their equivalents. These polymers are commonly called nylons. The name nylon is given to these fibers since the most common nylon 66, was simultaneously prepared in New York and London. Nylon 66 preparation. It is manufactured by the condensation polymerization of adipic acid and the hexamethylene diamine. The acid and the amine first react to form a salt which when heated at 525 Kelvin under pressure undergo polymerization with elimination of water as steam and the nylon is produced in the molten state. It can then be cast into sheets or fibers by passing through the spinrette. Nylon 66, since both adipic acid and hexamethylene diamine contain 6 carbon atoms. Uses. Unlike cotton fiber, nylon fiber do not rot, have high tensile strength, tough abrasion resistant, somewhat elastic. Further, nylon fiber are so much stronger than the natural materials then can be made much thinner. The availability of strong thin thread made possible nearly invisible woven stocking called nylons. Being tough, nylon is used as a substitute of metal in bearings and gears. Wrinkled nylon fibers are used in making elastic hairstring. Nylon 610. Another commonly used nylon is nylon 610, which is obtained by the condensation of hexamethylene diamine and C-basic acid, a dibasic acid. Another commonly used nylon is nylon 610, which is obtained by the condensation of hexamethylene diamine and C-basic acid, a dibasic acid containing 10 carbon atoms. Nylon 6 or purlone. Nylons can also be prepared from single monomer having potential amino group at the one end and a potential carboxyl group at the another end. For example, monomer capro, caprolactam and on polymerization give nylon 6. Caprolactam for the purpose manufactured from cyclohexene and described below. When the caprolactam is heated with a trace of water, it undergoes hydrolysis to give E-amino caproic acid, which upon continued heating undergo polymerization to give nylon 6. It is manufactured by the most of the industries in India and it is called nylon 6 since the monomer contains 6 carbon atoms. The filaments of nylon 6 are obtained when molten polymer is forced through a spinrod and the fiber formed are cooled by the steam of air. Phenol formaldehyde resins. Phenol formaldehyde resins preparation. The reaction between the phenol and formaldehyde has been used for the manufacture of an important group of polymer commonly called phenol formaldehyde resins such as Novolac and Bakelite. When phenol is treated with formaldehyde in presence of an acid or a basic catalyst, it undergoes a condensation polymerization to form either a linear or a cross-linked polymer called phenol formaldehyde resin or Bakelite. The process actually involves the formation of methylene bases either at ortho or para position or both at ortho and para position with respect to a phenol group. The initial product is a linear polymer called Novalac and which upon further heating with formaldehyde undergo criss-cross linking to form an infusible solid called bakelite. Soft bakelites with low degree of polymerization are used in binding glue for laminated wooden planks and in varnishing and lacquers. High degree polymerization led to the formation of hard bakelite, which is highly cross-linked thermosetting polymer, which is a starchy and water resistant polymer and hence is used in the manufacture of comb, formica tabletops, fountain pen barrels, gramophone records. It is also possesses excellent electrical insulating property and hence used in making electrical goods. Sulfonated bakelites are used in ion exchange resins, urea formaldehyde resins. In the presence of either acid or basic catalyst, urea and formaldehyde undergo condensation to form three-dimensional polymer called urea formaldehyde resins. The reaction involved are similar to those in the case of phenol and formaldehyde resins. In other words, the reaction actually proceeds through the intermediate formation of monomethylurea dimethylurea. The low molecular mass and branched polymers are first formed. The interlinking of molecules take place during the molding to form the three-dimensional resinous product. Uses in the manufacture of laminates such as formica and adhesives, in manufacture of tray and other kitchenwares. In solution form, they are used to increase the shrink strength of cotton and wood, etc. Epoxy resins, polyoxymethylene glycol. Preparation. It is an addition polymer and is obtained by the polymerization of ethylene dioxide in the presence of water or ethylene glycol and sodium hydroxide as a catalyst. Properties. These are water soluble polymer which are widely used in the preparation of cosmetic, pharmaceutical and lubricants. Epoxy resins preparation. These are the thermosetting polymers and are obtained by the reaction of epichlorohydrin with bisphenol A in presence of a base. The polymerization begins by the initial attack of phenoxide ion and the epoxide ring, followed by the elimination of a molecule of HCl to regenerate the epoxide ring. Properties and uses. Epoxy resins have an excellent adhesive strength and are used in the manufacture of electrical equipments, in laminating materials, and for flooring. Polyurethanes. A urethane is an ester of carbamic acid. The carbamic acid themselves are unable quickly decomposing to give amines and CO2. However, their esters, that is urethane, are quite stable. These are prepared by the nucleophilic addition of alcohol to isocyanates. Preparation. Polyurethanes are condensation copolymer. These are prepared by the reaction between a diol and a diisocyanate. The diol can be either ethylene glycol or some low molecular weight polymer with CH2OH group at the ends called prepolymers. Diisocyanate is usually toluene 2,4-diisocyanate. A number of different types of polyurethanes can be prepared depending upon the nature of polymeric alcohol used and the degree of cross-linking achieved. Even the diol used may be a polyester having CH2OH end group. In such cases, the structure of a polyurethane polymer may be depicted as follows. Polyurethane foams are produced when small amount of water is added during polymerization. Water adds to an isocyanate group, giving carbonic acid, which spontaneously loses CO2, thereby producing the foam bubbles or foaming. Properties and uses. Polyurethanes have a low degree of cross-linking and are quite soft and elastic. They are used for making stretchable spandexes and lycra fibers used for bathing suits and leotards. Natural and synthetic rubber. Natural rubber. It is a natural polymer which is obtained from the latex. Latex is a milky fluid which exudes from the rubber tree. When an in season is made in the bark of rubber tree found in tropical and semi-tropical countries such as South India, Indonesia, Malaysia, Sri Lanka, South America. Latex is colloidal solution of rubber particles which is coagulated by adding salts and acetic acid. The coagulated material is passed through rollers to make sheet structure. Chemically, natural rubber is a 1,4 additional polymer of isoprene. Since each repeating unit is a polyisoprene containing a double bond, it may have either a cis or trans orientation. Actually, in natural rubber, all double bonds have a cis stereochemistry. In other words, natural rubber is a cis polyisoprene. In contrast, synthetic rubber obtained by free radical polymerization of isoprene is called a trans configuration. Vulcanized rubber. Inspection of the structure of natural rubbers. Vulcanized rubber. Inspection of a structure of a natural rubber reveals that there are no polar groups or substituents, and hence intermolecular forces of attraction are only weak van der Waals forces. These forces are further weakened because of the cis configuration of all double bonds, which does not allow the polymer chains to come close enough for effective interaction. The cis polyisoprene does not have a straight chain but has a coiled structure. As a result, it can be stretched like a spring. On stretching, the molecules become partially aligned with respect to each other, and on withdrawing the force, the chain come back to their original coiled state. Natural rubber is a soft and tacky and becomes even more so at high temperature and brittle at low temperature. Therefore, rubber is generally used in the temperature ranges 283 to 335 Kelvin, where its elasticity is maintained. It has a large water absorption capacity, has low tensile strength and resistance to abrasion. It is also not resistant to action of organic solvent and is also quickly attacked by the oxidizing agents. These properties can be improved markedly by a process called vulcanization. It consists of a heating raw rubber with sulfur at 373 to 415 Kelvin. Since this process is slow, therefore additives like zinc oxide, 2 mercaptobenzothiodiazole, 2,2-dithio-bisbenzothiazole, tetramethyl urum, thiurum, and disulfate, etc., are used to accelerate the rate of vulcanization. The vulcanized rubber thus obtained has excellent elasticity, low water absorption tendency, and resistance to the action of organic solvent and oxidizing agents. During vulcanization, the sulfur bridges are cross-linked between the polymeric chains and introduced through their reactive allylic positions. The cross-linked make rubber hard and stronger and remove the tackiness of natural rubber since the individual chains can no longer slip over the other but are instead locked together in a giant sized molecule. The extent of hardness or toughness, however, depends upon the amount of sulfur added. Thus, about 5% of sulfur is used for making tire rubbers, 20 to 25% of sulfur for making ebonite, and 30% sulfur for making battery case rubber. The process of vulcanization was discovered by Charles Goodyear in 1839. Synthetic rubber. Methyl rubber. This was the first commercial synthetic rubber produced by Germany during the World War I. It involves polymerization of 2,3-dimethyl-butadiene obtained by the dehydration of pinacol. Cis-polybutadiene, cis-polyisoprene. Polymerization of 1,3-butadiene in presence of Ziegler-Natta catalyst gives cis-polybutadiene in which 1,4 addition occurs in which butadiene molecule and the remaining double bonds are whole. Cis. This polymer has a property similar to those of natural rubber and can be vulcanized in the same way. Styrene butadiene rubber. It is a copolymer of butadiene and styrene and is produced by the free radical polymerization. It is also called Buna-S because originally it was prepared by anionic copolymerization of butadiene and styrene in presence of sodium. Because of the presence of double bond, physical properties of SBr can be further improved by vulcanization properties and uses. It is very tough and good substituent of natural rubber. It possesses high abrasion resistance, high load bearing capacity, and is used for manufacture of auto tires. It is used for making floor tiles, footwear component, and capable insulation. Bubble gums containing styrene butadiene polymer. Buna nitrile rubber. It is a copolymer of 1,3-butadiene and acrylonitrile and is prepared by free radical polymerization uses. It is used in making oil seals, manufacture of hoses and tank linings. Butyl rubber. It is an addition copolymer of isobutylene and isoprene and is prepared by cationic polymerization properties. And uses. Butyl rubber is used to make automobile inner tubes and tire liners. Neoprene is a polymer of chloroprene 2-chloro-1,3-butadiene. Preparation. Chloroprene polymerized very readily. No specific catalysts are needed, but the polymerization is slow in the absence of oxygen. Chloroprene needed for the purpose is obtained by the addition of HCl to vinyl acetylene in accordance with Markovnikov's rule. Vinyl acetylene itself is prepared by the dimerization of acetylene by passing it through the aqueous solution of ammonium chloride and cuprous chloride at 343 Kelvin. Acetylene reacts with the two molecules of CH3 CH triple bond CH at 343 Kelvin. NH4Cl and CuCl gives vinyl acetylene, which on Markovnikov's addition with HCl gives chloroprene. Properties and uses. Neoprene is inferior to natural rubber in some properties but superior in its stability to aerial oxidation and its resistance to oil, gasoline, and other solvents. It is therefore used in making the manufacture of hoses, shoe heels, stoppers, etc. It is also used for insulating and for making conveyor belts and printing rollers. Thank you.